Closing out our research presentations for the conference, we have Sean Sullivan, who will be presenting on exit velocity over expected. Sean, take it away.
Hey, good afternoon, everybody. Can you hear me?
Yep, sure can.
All right, let me share my screen and we will get right at it. Okay, everyone, thanks for sticking through. That was an awesome presentation there by Joshua. And I'm very happy to have the opportunity to close out the 2022 SABR Analytics Conference. So without further ado, my project is Exit Velocity Over Expected, an evaluation of MLB batted ball data. My name is Sean Sullivan, and I initially created this project as part of my capstone project for the Masters of Data Science that I completed at DePaul University a year ago. I currently am a data scientist at a retailer in the Chicagoland area. And I also have a sort of passion project that goes in line with this project. I do some sports analytics research projects that I host online on my blog, Analytics. And I also have a Twitter account associated with that blog. And I hope that people will go and check it out because it's not so much my own work, but I also make an effort to share other analysts' work that I find on Twitter. I also post a lot of jobs that I find that live within the sports data world. So that's a brief introduction on me, and we'll get straight into the project. But first, we're going to talk about what I'm going to talk about here today. We'll go into an introduction into the project. We'll talk about the data that was used. We'll briefly discuss some of the methodology, and then we'll get into the real meat and potatoes of this, which is the results. So diving right in, we want to understand, right, exit velocity. And to really get a better understanding of why we're talking about that, we need to first discuss why it's important to batted ball events. We know that hitting is very difficult, and I think that this was a really great GIF to show just how tough it is, right? To be able to watch a pitch come out of a pitcher's hand and be able to determine what pitch type it is and where it's going and things like that. But not only that, we know that the speed of pitches has been increasing within the last 15, 20 years. The average velocity has been increasing. We know that there's been an added emphasis on the sort of pitch design, the pitch lab aspect of player development and pitching development. So we want to try and understand how can we combat some of these advances that pitching has made in the last few years. And I think for hitters, it's about sort of understanding how you can use that to your advantage. And getting into that sort of level is why I'm talking about exit velocity. I'm assuming many people here are familiar with what exit velocity is, but for those who are not, exit velocity is how fast in miles per hour a ball is hit by a batter. And this was initially starting to become captured by the Statcast technology that was implemented in 2015 by Major League Baseball. Exit velocity is not the only metric that is currently being captured. Other things such as launch angle, spin rate, and there's other metrics that are being captured, not only regarding the ball and the measurement of the baseball, but also the movement of players and other metrics associated with that. But why do we care about exit velocity? As I said, right, hitting is difficult. We know that pitching has been improving, and it's important to understand the sort of interaction between that. And with that, we can dive in a little bit further and realize that, hey, typically the harder you hit a ball, the more likely it is to be an advantageous outcome of a batted ball event. On the left here, you see a sort of bucketed range of exit velocities and the associated batting average with them from the 2021 season. You'll notice that once you hit that 90 miles an hour exit velocity and higher, you start to see a more and more likely advantageous outcome, a base hit basically, right? The harder you hit it, the more likely you are to get a base hit. And on the left here, you have a 2020 batted ball data, exit velocity on the x-axis, launch angle on the y-axis. And you'll see that sort of interaction between the dark blue, which is a successful base hit, that we notice between launch angle and exit velocity. And actually on that right-hand side, that little bubble of dark blue on the upper right-hand side were typically home runs, where you see that nice ideal combination of exit velocity over 100 miles an hour and launch angle in that 25, 30, 40 degree range. And I kind of already mentioned this, but this is what a lot of hitters are going for. They're trying to sort of, they're trying to make sure that the exit velocity and sort of launch angle off their bat are leading to more advantageous batted ball outcomes. So why should we care about exit velocity, I kind of think for two reasons. One, we already know that teams deploy very in-depth scouting reports, but getting a better understanding of how well a batter hits the ball harder than you would think, or maybe how much softer a pitcher reduces the exit velocity than you would perhaps think, can help go into play with certain in-game strategic decision-making. And then at a higher level, I think that it could also potentially be used as part of an equation for your roster construction, right? If you understand that certain players maybe perform very well against a player type that the teams in your division have on their team, then you could use that to try and combat some of the certain strategic decisions that your opponents are making. So all that blabber about exit velocity, what is this project? Why do we care about it? So exit velocity over expected is a metric. And what it is I am predicting exit velocity of a batted ball event, and I'm comparing that to the actual exit velocity of the batted ball event. So I'm using data from Statcast. I'm using a machine learning algorithm to predict the actual numeric value of an exit velocity. And then I'm using that to evaluate player performance, both for batters and for pitchers. So the way this works is, as I feed the data into this algorithm and it spits out a prediction of exit velocity, I'm comparing the actual exit velocity to the predicted. If the actual exit velocity is higher than the predicted, that means that the player did better than expected, which is seen as a good thing. The opposite is then true, where if the actual exit velocity is softer than the predicted, that would indicate that the player did not do as well as hitting that ball as would be expected. And with that, we're able to evaluate the player performance of both batters and pitchers. So let's get into the data a little bit. I know a lot of people have been talking about Statcast, and this might be a bit repetitive, but Statcast was implemented in 2015 throughout all Major League Baseball stadiums. It measures pitching, hitting, base running, and fielding, and it's a combination of camera and radar technology. I know that in 2020, they also implemented Hawkeye, which improved some of the measurements that Statcast was taking, and I thought that this screenshot here was a good insight and indicator into some of the things that are being captured outside of more obvious ones, like how hard a pitcher is throwing the ball, the spin rate of a pitch, the exit velocity, the launch angle. Where you see a screenshot here from a Red Sox game where Mookie Betts makes a crazy play on the ball, right? And you see his reaction time, you see how fast he was running, you see the distance covered and the route efficiency. So there's some really interesting things being captured by Statcast that's allowing teams and researchers alike to gain insights that they never had before. But how did I get my hands on this data? Well, really, I owe this all to two different parties. One, the folks at Major League Baseball who are hosting their Statcast data at a website clearinghouse called BaseballSavant. And then there's also some folks that developed a Python package called PyBaseball. And PyBaseball is wonderful. It allows you to query a variety of baseball statistic websites, but they specifically also have a functionality that allows you to query BaseballSavant. So a game happens, Statcast data is recorded, it gets pushed to BaseballSavant, and with that, you're able to query it with the PyBaseball package on Python. I do want to note that there is a similar package on R called, I believe, Baseball R by Bill Petty. So it mimics that in many ways in its functionality. So let's talk a little bit more about what I did once I grabbed data from Statcast through the PyBaseball package. Well, I only wanted to focus on batted ball events. So with that, I filtered out anything that didn't end in a batted ball event. Also remove what I'm calling leakers, which in this case, there's a variety of fields that perhaps would indicate the success of a batted ball event. For example, there were some measurements in some fields in the Statcast query that tells you the coordinates of where a batted ball event landed on a field. So coordinates further out indicating, a home run or a deep fly ball would certainly indicate how hard a ball was hit. So anything that perhaps was a little too indicative of the outcome of exit velocity that I was trying to predict were removed. And then thirdly, I had to address what are known as no nulls, which we'll get into here in a second. But all three of these were very important to getting the data prepared and ready for modeling. So what is no nulls? Well, in 2015 through 2019 season, Major League Baseball with the Statcast technology has had some difficulties in capturing all the measurements for every batted ball event. There was some research done I don't have the names of these researchers off the top of my head, but there was some research done and published online that came to suggest that Statcast perhaps was missing exit velocity and some other measurements of batted ball events, and there was some imputation done by the folks at MLB to take care of this missing data. And what I mean is there are certain batted ball types, so pop-ups, very sharply hit pop-ups, as well as balls hit hugging the foul lines, were not being properly captured in every sort of metric that was being measured. So things like exit velocity, and I can't remember the elements off the top of my head, but exit velocity in particular was particularly impacted by the Statcast technology not capturing the data properly. So with that, they used a technique to try and make an educated estimate as to what that exit velocity would have been with some of the other inputs that they were still measuring. And with that, they applied a sort of value to any batted ball event that was missing exit velocity. And you really don't see this if you just look at a sort of distribution plot of exit velocity by the occurrence of them, like a count on the y-axis and x-axis being the exit velocity, unless you split into batted ball types. So when you split by ground balls, line drives, fly balls, you start to see these values really pop. And that is what is on the left-hand side here with the 2017 ground ball exit velocity distribution. You'll see that there seems to be something fishy going on with this distribution of data. But when you remove that, and these researchers that I mentioned came up with a couple techniques for taking an educated guess as to trying to identify the observations that may have been initially missed and thus imputed with this approach by Major League Baseball. So using that same strategy, I removed potential no nulls. And that is what you see on the right here is you see that same 2017 ground ball distribution data with no nulls removed. So getting into some more characteristics of the data, what I did was I trained my machine learning model and tested it on 2017 through 2020 MLB batted ball data. And then I took that trained model and applied it through with the 2021 batted ball data. So you can see that here are the dimensions of the model that it was trained on, about just over 387,000 rows and just over 122.7 thousand rows for the application of the 2021 data. It was a mixture of numeric and categorical variables, and I was ultimately trying to predict exit velocity, which is a numeric value. So with the data in hand, it's important to talk about what questions I had and what my sort of mission was with this project. Why did I want to use machine learning to try and evaluate exit velocity in batted ball data? So the research questions were, is exit velocity over expected a metric that provide insight and value for evaluating MLB players? And then I also wanted to take it a step further and use an unsupervised machine learning technique such as clustering to try and see if I could identify any players that perhaps were being overlooked or potentially underutilized. And would that allow for interesting insights to be gained? So some details on exit velocity over expected, right? Before using clustering or anything like that, I first needed to create this metric. So to predict a numeric value, it's a regression analysis. So given the inputs of a pitch like speed, spin, location it crosses the plate, could we accurately predict exit velocity? And for this, I explored this problem with a couple different algorithms, linear regression, random forest regressor, extreme gradient boosting, and an MLP regressor. And we'll get into the results here in a second. But again, this was a regression analysis. I was trying to predict a numeric value, and I was essentially taking the residual of what the actual and the predicted difference would be to use that as evaluation. Long story short, it ended up being that the XGBoost regressor was the highest performing model. The R squared was 0.41, so decent, pretty solid. The MAE though, the mean absolute error, was at 8.48 miles per hour. So my big caveat with this project is the error rate is not as tight as I would like it to be. Full caveat, absolutely admit that. If this was a project that dealt with higher stakes situations such as modeling cancer or something with a little bit more importance, I would not want to necessarily use this model. But I think that since this is early on with Statcast data, this is an initial attempt at trying to understand and model exit velocity, that it is okay to use that moving forward and thus seeing if we could evaluate baseball players with this metric. And then for clustering, I use some dimensionality reducing techniques to help kind of cut down on some of the extension of the features that were used in the clustering. And I use k-means clustering to group players based on similarities. But this worked a little bit differently, where I used the average exit velocity over expected. So again, that difference between the predicted and the actual exit velocities of a batted ball event, but aggregated over the course of a 2021 season. And I use that with some other offensive aggregated statistics like weighted runs created for the 21 season, OPS, batting average, things like that. And with that, I was able to cluster and find 4 distinct clusters, and we'll talk about one of them in a little bit here. So getting into the results, which are a lot more fun than talking about the ins and outs. So like I said, I trained and tested the model on 2017 through 2020 data. I then ran the 2021 batted ball event data through the model. And over that course of the season, I aggregated up the player's average exit velocity over expected on a batted ball event. You'll see here are the top 10 players for the 2021 season. Rafael Devers was at 7.27, meaning that on average, he typically hit a batted ball about 7.27 miles per hour harder than the model would have predicted. And you see some of the heavy hitters, right? You see Stanton, Guerrero, Ohtani, Judge, etc. And what I did was I looked at these results, and I wanted to also compare to the Statcast rankings in terms of average exit velocity, where they ranked percentile wise, where they ranked on max exit velocity, hard hit rate, things like that. And a lot of these really matched up well, which was an indication to me that despite some of that error that I was seeing in the model training and testing, there was still some direction and some significance here of this being an okay metric to continue with this sort of evaluation. And then the opposite could be said about pitchers, right? As I mentioned, hitters with a positive average exit velocity over expected would be seen as a good thing. Pitchers would want to go for the opposite. They'd want to try and limit the exit velocity that is being predicted and expected. And what you see here are mostly relievers, but if you were to up that filter on the batted ball event a little bit higher so that you can try and limit relievers and get in on some starters, that's when you would start to see, again, your starters show up a little bit higher in the rankings. So now that we understand what this model is, the outcome of it, some very top level results, who cares? Why is this useful? How can this be used moving forward? For this, I'm going to give a case study of Rafael Devers. As I mentioned before, he was the top performer for the 2021 season with an average exit velocity over expected at plus 7.27 miles an hour. And he was particularly strong and successful against a couple different types of pitches, changeups, sliders, and curveballs. And you see the associated average exit velocity over expected metric on the right. But not only did he hit the ball very hard, he hit many baseballs that were pitched out of the zone. About 24% of his batted ball events occurred in zones 11, 12, 13, and 14, so pitches that would have been classified typically as a ball. His average exit velocity over expected for batted ball events out of the zone was at plus 7.25, so right in line with his overall average. And he was one of the highest, he was one of the best performing players in terms of average EVOE for batted balls out of the zone. And here, as I mentioned, BaseballSavant, really great for different visualizations. And what you see on the right here is a sort of heat map with a strike zone that shows you the frequency for red being more observations, white a little bit less, and blue the least amount of observations for batted ball events. And you will see that he does have a decent amount of batted ball events on that sort of outside and low and outside ranges of the zone. And again, here are some other visualizations where you can see how he ranked in terms of average exit velocity, the percentile, right, the max exit velocity, hard hit percentage, etc. But then how would you use this as an opposing manager? Well, it sounds simple, right? You'd want to try and avoid where he's very successful. So maybe don't throw those changeups in the zone where he's typically having the most success with his batted ball events, so that where you see on that heat map the very deep reds, maybe avoid that. But despite some of his success on out of zone pitches and hitting them much harder than you would expect, he did still have a few weak points. In particular, I believe that sinkers low and inside out of the zone were some of his least performing, so the weakest batted ball events in terms of average exit velocity over expected. So you could use this metric to not only understand where he's successful, but also understand where you could potentially attack him. And what I think differentiates this from strictly just using, well, we can just look at his average exit velocity within the zones. I think where this differentiates itself is by telling you just how much better or worse he does in comparison to what would be expected. Moving on to the clustering insights, as I mentioned, there were 4 different clusters. We had a very high performing one, which are the purple that you see there. You sort of have your middle tier performers with the yellow and the blue, meaning they had an above average exit velocity over expected and a solid weighted runs created. But instead I focused on the lowest group that you see, where there was a wider range of average exit velocity over expected metrics, but lower weighted runs created for the 2021 season. And my reasoning for this was, I thought that perhaps with using a couple different ways to cut the data, maybe we could find a few interesting players that could say, hey, they need a little bit more playing time, or potentially need a little bit more time to develop, etc. And that's who I've decided to focus on today. So within that cluster, in terms of low weighted runs created and the sort of middle ground average exit velocity over expected, Alejandro Kirk, William Contreras, and I'm sorry, I can't see the other side of that, but the other player on the St. Louis Cardinals all showed up as interesting players because they all had average exit velocities over expected higher than the mean of their cluster. And again, I want to emphasize that the clustering wasn't just based on 2 features. There were a variety of, again, aggregated 2021 offensive features that were used for the clustering. So someone like Alejandro Kirk with a very high average exit velocity over expected and a pretty decent weighted runs created plus at 106, right? So 6% better than league average in 2021 would indicate that perhaps there's a player that deserves a little bit more playing time, a little bit more consideration. Someone like William Contreras, again, showing promise with a very strong average exit velocity over expected, but a slightly below average weighted runs created plus, which again could indicate maybe a little bit more playing time, or perhaps he just hits the ball very hard and doesn't have very much impact outside of that. And the same goes for the last player, where high average exit velocity over expected, where it was above the mean of that cluster, but his weighted runs created plus was very, very low. So that was a little bit more due to less playing time, and there was some success in the minor leagues for him. So again, an indicator of perhaps this player with more opportunity would have an opportunity to flourish. And maybe this is an indicator to that. So some final thoughts on the project. One, I do have all this data available in terms of an interactable dashboard. It's hosted through Google Data Studio. It's on this slide. I believe it's also on the GitHub that I have, which I don't have hyperlinked here, but if it's not, I'll make sure I get it up there today. And with that, you do see the overall rankings that I showed previously, but I do have a portion on the bottom that allows you to filter by player, and you could then see the sort of pitch types and locations of zone that they do well or do poorly on. And I have 2 different dashboard tabs, one for pitchers, one for batters. So if you're interested in that, I encourage you to go and check it out. And in terms of next steps, as I mentioned, I don't think that this is as strong as an overall metric as some of the others that have been presented today and presented over the course of this weekend. But I think that this serves as a fairly strong initial attempt to try to utilize exit velocity and try to model it and try to understand it a little bit better. I also think that it could serve as sort of an element of a composite score, perhaps integrated with something similar to what was presented just before me, with trying to quantify a sort of quality of an at-bat. You can look at how is their pitch selection, and then are they hitting the ball harder or softer than expected? That could kind of go into an overall metric such as that. And then in terms of non-EVOE related, I am interested in something that I'm currently working on, but I'm still in the very beginning stages, is quantifying bullpen management decision-making by MLB managers. So I am working on a variety of things I am very excited about, and I'm very excited about this project as well. So at this time, I'd like to open up to questions. I have my blog located on the left, my email address, the Twitter account that I mentioned. I'm also on LinkedIn, so I'd love to connect and learn more and work alongside with everybody. All right, let's see. So I do see some questions. Okay, so as looks like here's a question that's okay. So for Twitter, I do have the handle here. So it's uram_analytics. Again, I encourage you guys to check that out. I really don't have much of my own work featured on there. It's mostly current job postings that I've been finding and then sharing a lot of work from others on Twitter. Let's see, Dylan said, do you think broken bats could be a cause of the error being higher than you wanted? That's an interesting question. I don't necessarily think so. I think that one, it's difficult to quantify that sort of interaction between some of the inputs that I had, such as the speed of the pitch, the movement of the pitch, the spin direction. One of the features that was stronger in terms of feature importance, so more indicative of being able to correctly predict exit velocity, was launch angle, but even that correlation was only at 0.11. So I think really what would help improve the performance in the model would be a couple things. One, perhaps folks that are much more aligned with the physics of baseball than I am, having more insight and maybe say into some of the things that are being captured and publicly shared by Statcast. I'm sure that many teams and MLB itself has a lot more fields, a lot more interesting features that maybe could get a little bit better at pinpointing in the accuracy of this model. Secondly, I think that sort of additional feature engineering, again, leaning and partnering with people who are more educated with the physics of baseball, can suggest, hey, maybe you should look at it this way and create this field based off of this data to help pinpoint and get that sort of model performance improved. Because that's typically what I've seen in side projects and then things that I've handled at work that really add the most value. Is it's typically the data itself, not necessarily the modeling techniques. Could I post to GitHub? Yeah, I absolutely could. Let me grab that 1 second. I don't have it up with me, so I'm sorry. If you email me, or if you actually go to that website that I have hyperlinked here, you would see in the links tab over one of the tabs I have that shows the portfolio, there are links to the GitHub repositories. Okay, question from Eric. Thank you for the nice comment about the presentation. Have I thought about extrapolating or integrating with contact quality? That's actually a really interesting point. As I mentioned, this metric on its own is not anything that's going to blow anybody's socks off, right? But I do think that it could be improved and could be integrated into something, as I mentioned, like a composite score, working off of what Joshua Mold had done. Again, maybe getting into that sort of quality of contact. Absolutely. I think that this metric would probably serve much better use as a sort of element to a larger scale equation for evaluating a batted ball outcome or a quality of the bat outcome, or whatever whatever that may be. And then from Jeremy, thank you again for the nice comment on the presentation. Have I ever used data to predict future success for fantasy baseball or just for my own enjoyment? So I've never used data to try and get into fantasy, either baseball related or like, fantasy football or basketball or anything like that. This is sort of a byproduct of the master's program I was in at DePaul, where they encouraged us to use data sets that we were interested in to apply them to what we were learning in class as like a final project. So for a variety of classes, I've explored different baseball research problems, basketball research problems, things like that. And currently now, since I'm no longer in school, it's definitely more for personal enjoyment. That's really the sort of motivation behind trying to explore how to quantify a bullpen management decision by a manager. I've since, after creating this metric and seeing that, it's not the end all be all, it's really not super informative. So I have a little bit more of a fire lit under me to try and come up with something a little bit more innovative, a little bit more novel. And right now it's just for personal enjoyment. And then from Brian, isn't mean absolute error a function of the range between best and worst hitters? Let's see. I don't know if I have the best answer for that. The mean absolute error really is just, again, a good, evaluation metric to evaluate how accurate a regression model is. There's certainly discussion to go around, well, if a player exceeded, let's say 30 miles an hour over than what would be expected, is that just really good players driving up that MAE and then really bad players driving down that MAE? That would be something that I would need to evaluate a little bit deeper. And it's actually an interesting point to use. But I don't really have a good answer to say, like, is that what was actually happening? But again, good observation. I will certainly have to dig into that. Let's see. So am I treating 80 miles an hour over an expected 60 mile an hour, the same as hitting 100 over an 80 EVOE? Isn't the latter more useful in terms of generating better at bat result? Yeah, that's a yes. Current with this approach, I am treating them the exact same. And to answer your question, yes, I would think that that sort of over performance at 100 miles an hour versus 80 would be better. And that's a really good point, because that's another angle that could be used to sort of normalize or level set certain players that, you know, maybe they were doing a little bit better against very difficult pitches to hit, but they were only hitting them slightly above expected and thus had a positive average EVOE, versus that not really having much impact overall. And what I'm trying to say is you're absolutely right. That is an indication that could be used for normalization and trying to sort of level set just how good a player over or underperformed relative to the actual value of that batted ball event. Because as we saw, typically a hit is associated with a batted ball over 90 or so miles per hour. So very, very good and interesting comment there. Okay, that looks like all of the questions. Thank you very much for this opportunity. It was great speaking with all of you. So sort of a dream come true, and I'm very excited that people were interested enough to tune in and listen. So thank you.
Well, Sean, thank you. That was really interesting stuff. And I look forward to seeing more of your work in the future. So thanks for joining us today.